Hello, welcome back to General Chemistry 1. My name is Daniel, and in this video we're going to be looking at Lewis structures. So in the last video we looked at the energetics of bond formation as well as some of the mathematics of it. But in this video we're going to be looking at what's called Lewis structures. And that's just a method of drawing covalently bonded molecules, including their valence electrons, so that we can look at their bonding and as well as their valence electrons and what's going on in the covalently bonded molecule. So in the Lewis structure model, we're going to be using what's called the Localized Electron Bonding Model. Now there's two kinds of pairs of electrons in this model. The first one we have is bonding electrons. Those are just the electrons that are involved in making bonds. So if we look at a bond like this over here, that's 2 electrons in that bond. Each bond is 2 electrons. So in a double bond, there's 4 electrons because there's 2 of these lines over here. Each of them is 2 electrons. The other kind of electron we can have is a lone pair. A lone pair electron is centralized on an atom. So if we look over here, these are a lone pair of electrons, like that. So those aren't involved in the formation of bonds. Now, important thing to note with the localized electron model is that electrons are, for the most part, always going to be in pairs of 2. So you're very rarely going to have a lone electron. There are a few exceptions that we'll get into later in the video. But for the most part, that's a pretty standard rule. So what a Lewis structure actually is a representation of the valence electrons of a molecule. So as we know, valence electrons are just the ones that are in the highest energy orbital, the highest energy principal quantum number. That's the quantum number n. So if we look at an ionic molecule like this, KBr, what's going to happen is there's going to be the formation of potassium cation and bromine anion. As we know, in an ionic bond, there's going to be a transfer of electrons between the two species. So what's going to happen then is the Lewis structure will look something like this. We're going to have K plus with no valence electrons and Br minus with 8 valence electrons. So the reasoning for this, we can look at that through electron configurations. So for K plus down here, it has a noble gas configuration of argon. It's also equal to neon 3s2 3p6. Bromine's the same way. It has the noble gas configuration of krypton. So one of the biggest motivations in drawing Lewis structures is we want every atom to have a full valence shell, a noble gas configuration. And one of the things that we can do to make that happen is form what's called octets of electrons. So the octet rule, as it's called, can be summarized like this. In general, in a Lewis structure, we want all the atoms to have 8 valence electrons on them. So as we see in bromine, there's 4 sets of lone pairs. 4 times 2 is just 8 electrons on the bromine. And that gives it that full valence electron shell. So if we look at, we can jump right into making Lewis structures. So first off, we can look at the first element, hydrogen. Hydrogen is an exception to the octet rule. The reason for that is because, as we know, there's no 1p orbital. So a full valence shell for hydrogen is just that of helium. And that's equal to just 1s2. So what's going to happen in Lewis structures is hydrogen's always going to form just a single covalent bond, just having 2 electrons attached to it. So then we can look at helium. Helium already has a noble gas configuration. And so that means for the most part, helium is never going to form compounds, because why would it transfer electrons? Why would it gain or lose electrons when it already has that stable noble gas structure? When we get that further down to the periodic table into period 2 and 3, what we can do is we can assign a number of valence electrons per atom based on its position on the periodic table. So that's just going from left to right. The group 1 atoms have 1 valence electron, group 2 has 2. We skip over the transition metals. We're not really going to deal with them when we're looking at Lewis structures. We go to group 13, it has 3. Group 14 has 4, 5, 6, 7, 8, so on and so forth. So you see the basis of the octet rule then is the fact that there's 8 valence electrons on those noble gases, and we want to get a noble gas configuration for all of our atoms in a system. So how do we go about writing a Lewis structure? Well, we can break it down into a list of steps. First off, we're going to count the number of valence electrons in the total molecule, and that's just going to be based on the graphic I just gave you in the last slide. We're going to see how many atoms there are. We're going to count up the valence electrons of each one and add them up. Next, we're going to connect all the atoms with single covalent bonds just to start with. We'll get into how to connect those in the next slide. But we're going to connect them. We're going to have a central atom most likely. As I said, we'll go into that in the next slide. So once everything's singly covalently bonded, next thing we're going to do is we're going to count how many electrons are in the structure. We're going to count up how many lone pairs there are, how many bonding pairs there are, and that's going to be the total number of electrons in our structure. So we're then also going to assign lone pairs to everything to fulfill the octet rule. So for example, if I had a bond like this to start with, I would fill up their octets by giving them 6 lone pair electrons each. Then we count how many electrons there are. So here there's 2, 4, 6, 8, 10, 12. This structure has 14 electrons in it. So next up, we're going to compare how many valence electrons there were in the structure. And if that's different from the number that we get when we do a single covalent bond with lone pairs, then what we have to do is we have to form double bonds and triple bonds. I'll demonstrate that in an example in a few slides. So then we're going to continue doing that until the number of valence electrons that we calculated for a molecule equals the number of electrons in the Lewis structure. And then we're just going to check our structure and make sure everything looks good. So we're going to get into some examples, but first let me explain to you how to connect atoms. So as we said before, hydrogen's always going to form these single covalent bonds, like so. And you're never going to put lone pairs or anything like this on the hydrogen. As we said, that's just because it's S2. So don't do that. Just that. Next up, a general rule is that the halogens are pretty much always going to form single covalent bonds, but they're going to also have 6 lone pair electrons. So if I had a carbon-fluorine bond, I would fill this fluorine with 6 lone pairs. That's generally a stable way of having a halogen come out. And then carbon's also pretty much always going to have 8 bonding pairs, or 4 bonds. You're rarely going to see lone pairs on a carbon. It'll more likely look like this. For example, if we had methane, it's always going to have just those 4 bonds. Now, for any other molecule, we can have 2 kinds of atoms. We can have a central atom and a branch atoms. So in a structure like SF6, for example, we see there's 1 sulfur and 6 fluorines. Since there's a singular sulfur, we can assume that it's the central atom and fluorine are the branch atoms. So the structure for sulfur would generally start out looking like this. You would put sulfur in the middle, and everything else attaches to it as a center. If that doesn't work, we can generally write out the bond structure based on how a molecule is written. So for example, in SCN, that's just written in the order of bonds. So SCN would start looking like this: S bonded to C, bonded to N. So it wouldn't be S or C, N, S, or something like that. You're going to just do it based on how it's written. And then if that doesn't work, what we can do is we can look at the formal charges on each atom and determine the best kind of order to bond things in. We'll get into formal charge later in this video. But for now, let's start getting into Lewis structures. So let's look at a basic molecule, water. So if we count up the valence electrons, we know oxygen has 6 valence electrons. Each hydrogen has 1 valence electron. Times 2 is just 2 valence electrons. So water has a total of 8 valence electrons. So now we can start and draw out the bonds. So O is the singular atom, so it's going to be in the center. O bonded to an H.